global warming, not pollution. It is us ignoring the future. For a better tomorrow, BVRIT found a way to save energy, fuel, CO2 and green by using solar energy. This will have its impact on their generations to come. Remember, we only have one.
Our perspective is different. As our perspective is different, our outcomes are also different. Be the difference.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message, and the word choice is bland.
Shravan sir, good afternoon, sir.
Very good morning. Naresh sir.
Sir.
Sir, the sir will come within 5 minutes.
Okay, sir.
Okay, we'll start 1:35.
Okay,
Just
sir.
now I spoke to resource person.
Okay, sir. You can play the video, sir, regarding that. Okay.
Sure. I will play them.
Hello. Hello, sir. This is Vijayakumar, resource person.
Hello, sir. Sir, good afternoon.
Can I take 5 minutes to join back? So that's what just I logged in.
Okay, sir.
So
Okay, sir.
okay, sir. Sure.
Okay.
Hello.
Hello, sir. Very good afternoon, sir. Vijayakumar, sir.
Sir. Yeah. Good afternoon, sir.
We'll start the meeting. Otherwise, wait for another 2 or 3 minutes. Your wish only.
I mean, if we are okay, then we can start. Otherwise, we can wait.
Okay,
Suppose
sir.
if we have
Okay, sir. We'll start the
informed.
meeting, sir.
Yeah, sure, sir. Sure.
First
Sir, how can I share my slides?
Already, I will given presenter option to you, sir. In top right corner, some video and unmute your audio. This option is available now, sir. Next
Yeah,
to this one, it's time one up arrow is there now, sir.
I mean, it shows a desktop window screen share.
Yes.
Instead of screen share, can I able to share my only that window? I mean, only the presentation.
Yes, sir. Yes, sir. It's accept them, sir.
Because
first to open your PPT, sir. PowerPoint presentation.
Yes, sir. It's okay. I'm getting it now, sir.
Okay, sure. Mr. Mahesh, sir. Mahesh, sir. Mr. Mahesh, sir.
Yeah, sir. Is it audible, sir, my voice?
Yes, sir. It's audible, sir. Mahesh, sir. Sir, Vijayakumar, sir, with the PowerPoint is showing, sir. It's visible only, sir.
Yeah, sure, sir. Sure.
Correct. Sir, please move for the next slide.
1 minute, sir.
Okay, sir. Sure.
Yeah.
Okay,
is it fully visible, sir, or is there any issues?
No, sir. The last nearly it's having bottom part. It's not visible, sir.
Okay.
Yes. Presently, it's okay, sir.
Okay.
Okay, sir. So very good morning, Vijayakumar, sir. Very good afternoon, Vijayakumar, sir. First of all, I thank you for accepting our invitation and delivering the lecture for our IICT sponsored STTP program. Mr. Mahesh, sir, please introduce our today resource person, Dr. K Vijayakumar, IIIT Kancheepuram, Tamil Nadu.
Sir.
Sir, Mahesh, sir, your voice is...
Kumar, sir.
Okay, sir. Presently, it's okay.
Sir, now it is okay.
Now it is okay, sir. You continue, sir.
Yeah, good afternoon, one and all. I am very happy to introduce today's session speaker, Dr. K Vijayakumar, sir, Assistant Professor, Department of IIIT, Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, Tamil Nadu. Dr. K Vijayakumar sir, he graduated from Coimbatore Institute of Technology, Coimbatore, and his master program from National Institute of Technology, Trichy, and he received his doctoral degree from National Institute of Technology, Trichy, and his postdoctoral fellow in electrical engineering from Nanyang Technological University, Singapore. Sir, having the various research interest projects in the area of industrial electronics and control, smart grid, power electronics and electrical machines, fax controllers, artificial intelligence, power conversion techniques for wind and sir has published various IEEE and IIT journals, around 11 international journal IEEE and IIT papers has published, and he presented many conferences, IEEE conferences and national and international conferences, many. He attempted or he organized the programs also, and sir has various research projects is going to get that in the research guide of in the field of design and development of power electronic converters for wind and PV systems, and analysis and design of switched mode power converters for renewable power generation, analysis and performance enhancement of hybrid wind PV system with certain power electronic controllers, investigation on certain controllers and energy management system for this grade. And sir having the many research projects given by the SERB Government of India, MCIT Government of India, and Minister of Renewable Energy Government of India, Shastri Indo-Canadian Institute. So he has performance enhancement and reliable operation of wind PV distribution system supplying AC/DC load with remote condition monitoring around 20 lakhs from 2016 to 2019 given by SERB DST projects, and design and development of power electronic converters for renewable powered telecommunications system around 37 lakhs from 2016 to 2021 offered by Ministry of Communication and Information Technology Government of India. Design and prototype development of efficient wind driven doubly fed induction generator PV hybrid system with a smart controller for reliable supply to isolated lands, 30 lakhs 2017 to 20 offered by Ministry of Renewable Energy Government of India. And development of technologies in area of renewable energy around 2 lakhs in the year of 2018 given by Shastri Indo-Canadian Institute. And sir is having many awards and honors he has. So he has POSOCO Power System Award for doctoral thesis and listed top 10 among all IITs and NITs for PhD thesis given by POSOCO and Indian Institute of Technology IIT Delhi in the year of 2014. And sir is selected for Canadian Commonwealth Research Fellowship in the University of Saskatchewan, Canada for a research award given by Canada Bureau of International Education in the year of 2013. And postdoctoral fellow from Nanyang Technological University, Singapore for postdoctoral research given by Nanyang Technological University, Singapore 2012. GATE Research Scholar for year of 2007. And MHRD Fellowship for PhD for fellowship given by Ministry of Human Research Development, Government of India 2009. Young Scientist Award for Startup Research Grant given by SERB DST Government of India. Young Faculty Fellowship for Research Project Grant given by Ministry of Communications and Information Technology Government of India 2016. And sir has a visiting professor for research given by University of Saskatchewan, Canada 2017. And Shastri Indo-Canadian Fellow for Research Collaboration given by Shastri Indo-Canadian Institute, CIDA and MHRD in the year of 2017. And sir also IEI Young Engineer Award from 2017 to 18 for excellence in the field of electrical engineering given by Institution of Engineers in the year of 2017. So now I request Dr. K Vijayakumar sir, please take over the session and deliver the valuable information to our participants. Thank you very much, sir.
Yeah, good afternoon to all. Thank you very much, sir, for for the very detailed introduction of mine. With that, today's talk, we are going to discuss about power electronic controllers for wind energy conversion system. As I have seen your brochure, the theme of that course is development and entrepreneurship in green and smart grid technologies. So here, when we come into that wind energy conversion system, this wind energy conversion system is a part of renewable energy sources. And when we discuss about the development happen in the wind, it's a part of your smart grid, or you can say it's a microgrid, or you can say it's green energy products. So in any aspect, you can think of it. So here, what I want to convey here is when we are discussing about the smart grids, in a smart grids, just we are having the distributed generation resources. So here in a smart grid, you can able to communicate with each other, not only among that DGs, even you can able to communicate with the load centers, as well as generation units, even with the discoms, transco, and everywhere. It's you can have the communication among all the participants in the system. So that's what now we are calling as a smart grid. So when we are trying to modernize this existing microgrid or our grid, that will be called as a smart grid. So whatever you are talking about the technologies, it's revolving around this components. So that's what just I have chosen power electronic controllers for wind energy conversion system. In a light note, I can say it's a wind energy conversion system. So when we talk about wind energy conversion system or photovoltaic conversion systems, mainly just we will focus on the power conditioning side. So power conditioning, I mean, already just they are manufacturing, I mean, already just we are in the growth of manufacturing the panels as well as manufacturing the turbines. Once if we are having these turbines and panels, how we can able to condition this output power from these panels and turbines, and that can be injected to the grid, or it can be utilized for the local loads. So that's what in this today's session we are going to discuss about the various power electronic converters and associated controllers for utilizing the wind energy. Okay, so here before just I can start my slide. So before going to that, just we will discuss about the energy transformation in the year of 2050. So the main objective of this energy transformation is for reducing the carbon emissions. So presently, just we are emitting a lot of gases from these conventional energy sources. So in a future in 2050, they are trying to reduce 70% of the gas emitted by these conventional power plants. So that's our main objective, one of the main objectives in the energy transformation. Then by having this renewable energy sources, you can able to reduce your energy cost. So we can say last 10 years back, if you have seen the cost of that wind or photovoltaic, it's around 8 rupees to 10 rupees per unit. But now even the companies are ready to sell their power for 2.75 rupees. So that's what it's a development happened. So that because of that, we can able to reduce our energy cost by incorporating the renewable energy sources. So at the same time, in economic point of view, just you'll get a gain. At least if you spend 1 rupees in future, you can able to get the 3 to 7 rupees from the resources, from the renewable energy resources. So that's what in economical point of view, we can say it will be benefited. And if you look at the energy security point of view, so energy security, what is the energy security? Why the energy security comes to our mind means, just if we are talking about the power generation stations or power generation plants. So the coal in a conventional power plants, you'll use coal or oil for generating the power. So this coal and oil we are importing from the developing nations or from the various countries. So if they stop due to that political issues, if they have stopped the exporting, then we will affect adversely because of this export bans. So that time, just we will be in the demand of the huge oil and coal. So for avoiding this, so once if you are not getting the coal, then you cannot able to fire your power plants. Even in India also, just we are having that coal mines, but whatever the coal we are getting from this mine, or it's not up to that mark to burn our conventional power plants. The grading is very less. So that's what we are depending upon the developed countries. So once if they stop the exports, then we will greatly impact on our power generation. So if power generation affects, then just we can think of it, every industrial can affect it, not only in the industry as well as our personal lifestyle. So we can say it's insecure with the fuels. So to avoid that, if we are having that renewable power generation in our nation, we can able to meet our demands. So that's what by having the renewable power generation installations, we can able to improve the energy security of the any country. So that's what they are expecting that, forecasting that 64% of the demand from the fossil fuels can be removed once if we are having the renewable power generation sources. And full energy access. So when we talk about the full, the slides are visible to you, audience? Is there any issue with the slides?
No, sir, it is visible, sir. It is visible, sir.
Yeah, sure. If you are having any questions or queries, you can interrupt me in between. No issue. If you have any doubts or if you want to interact with the particular topic, please let me know in between. So I'll be happy to answer your queries.
Thank you, sir.
Okay, so another important objective is the energy access, the complete energy access. Even in India, even we can say 8 to 10% of the villages are not connected to your electrical network. So if you are not connected to, if you are not connecting with the electrical network, that places can't able to access the electricity. So for that, in that places, we can have the renewable power generation sources like wind and photovoltaic to supply their needs. So just we can think about standalone standalone PV system or standalone wind energy conversion system. So because of that, every part of the country, even the nook and corner, can have the access of the electricity. So that's what we can say is 100% energy access. So by having this renewable energy technology, we can able to electrify the 100% of the households. So that's another objective by installing the renewable energy sources. Then by having this all the objectives, finally just we can come into the socio-economic point of view. So even if you are taking any kind of developments that's happened, that should be focused on the socio-economic development. So even this renewable energy renewable power generation also, we can able to create a lot of jobs. We can create a lot of job opportunities to the nation. So that's what just we are with this objective, we are having the energy transformation by 2050. So if you look at the estimation of the renewable energy by 2050, so this chart will give you the clear picture. So in 2016, just we are having the 25,000 terawatt hour of the, that means terawatt hour per year we are generating the power. So out of it, if you look at this yellow one in this point, the yellow one is very less. So even if you look at yellow and this one, blue one, is a very less in the composition. If you look at the 2050, in 2050, your the yellow and blue are larger portion. So this yellow and blue are renewable power generation. One is solar PV, yellow is for PV generation, and blue is for wind generation. So this renewable power generation contributes much in the total power generation. So if you assume it from here, if you look at that, as present 2016, so just we are having very less amount of the power generating from these sources. Even in the 2050, the yellow and blue are huge part. That means that we are estimating that at least 1/3 of the power should be generated from the wind energy conversion system. Then another 1/3 of the demand is met by the photovoltaic power generation. So by looking at this chart, we can say the renewable power generation will dominate in the power generation industry. So here I have taken the wind here. Why? Because just we are having the very mature technology in wind energy conversion system over the photovoltaic power generation. But in the last 5 years, or you can say in the last decade, there is a lot of development happening in the photovoltaic industry. So just we can that's what nowadays just we can able to see the 500 megawatt photovoltaic plants in the country. So here the cost of the panels, even if you have considered in 2010, the cost of the panel is huge. Even if you want to purchase the 220 watt panel, it's almost cost 70,000. So, but here the 200 watt panel is almost 10,000 rupees. So 7 times the price is decreased in terms of panel cost. At the same time, the power electronic converters also it's available for interfacing this photovoltaic system with the load or the grid. So another advantage with that photovoltaic systems are is a static system. So static system means in a photovoltaic, you do not have any kind of rotating parts. So you can use that photovoltaic panels in any application, even from the milliwatt to megawatt. But when we come into that wind energy conversion system, so in a wind energy conversion system, we are having the rotational parts. So because of these rotational parts, you cannot use it for the low power applications. I mean, I can say I cannot use it in my watch, or I cannot use it in my laptop, or I cannot use it in my any kind of electronic gadgets. But photovoltaic panels or photovoltaic cells, you can use it for all applications. Even the microwatt level also people are using for wearable devices or some kind of medical devices and all. But wind, you cannot use it. So the commercial wind turbines is ranging from if you want to the power demand more than 5 kilowatt to 10 kilowatt, then these wind turbines are the best option. So you can use it only for the bulk power generation. So that's what here we can say from 1985 itself, people are working on the wind energy conversion system. So here in this slide, I'm giving some milestone of the wind energy conversion system. In 1982, they have come up with the 22 kilowatt of the single wind turbine can able to generate the 22 kilowatt of the power. So single wind turbine rating is 22 kilowatt. Then within that 2 decades, they achieved the 1 megawatt range of 1 megawatt. Then if you look at that 2008, in 2008, almost they have reached the 100 gigawatt of the installed capacity. Only the installed capacity. It's not the power output from this wind turbines. So installed capacity means at least we can get 70% of the power from that wind power plant. So they have achieved the 100 gigawatt of the installed capacity. Then within the decade, if you look at the 2008 to 2018, within the decade, they have increased the 5 times in the installed capacity. Almost they can able to generate 564 gigawatt of the power from the wind turbines. So 2008 to 18, you can look at it, 5 times the installed capacity increased. So we can definitely see that there are a lot of job opportunities. It's available in the wind industry. Suppose if you are increasing from 100 gigawatt to 500 gigawatt means you can employ a lot of people in the development. So in 2019, a single wind turbine cost itself, it's a rating itself is a 10 megawatt. So the single turbine itself can able to generate the 10 megawatt of the power from the wind, right? So this is the developments it's happened in the wind energy conversion system. So when we come into the statistics of the wind energy conversion system, so the total generation mix, out of this total renewable power generation mix, in 2018, just we are having the 6% of the power is generated from the wind. But in 2050, they are focusing on 35%. That means 1/3 of the power should be come from the wind turbines. So here the total installed capacity in 2018, along with the onshore and along with the offshore, we can say almost 550 gigawatt. So as of now, just we are having the 550 gigawatt of the power is coming from the wind turbines. So that we can look at here, it's going to increase almost 10 times, right? It's going to increase 10 times. So almost we can able to get 6,000 gigawatt of the power from the wind turbines, right? So even every year the installation is keep on increasing. This is what this statistic shows. And when we come into the India, it's very important to discuss about the scenario. So in Indian scenario, almost we are having the 87 gigawatt of the power from the renewable energy sources. In 2019, up to 2019, 87 gigawatt of the power from the renewable energy sources. And they are expecting that in 2022, they are going to install 175 gigawatt of the power from the renewable energy sources. Here, renewable energy means wind and photovoltaic, both. So that's what even in India, just we are having the separate ministry for renewable energy, Ministry of New Renewable Energy, MNRE. They will provide the guidelines, even the regulation for this industry. So even just we can even there are a lot of entrepreneurship opportunities in renewable energy systems. So that's what they have, the two institutes, one for solar and another for wind. So one is NISC, National Institute of Solar Energy, which is located in the Delhi, and another one is NIWE, National Institute of Wind Energy. So that is located in the Chennai. So these two institutes, they are having a lot of research projects as well as commercialized technologies. So from this, even MNRE also, they are providing a lot of opportunities in the in terms of battery energy storage development, even the inverter developments, even you can say some household lights with the aid of photovoltaic cells. So these are the developments happening. Even the persons who are really interested in renewable energy, they can take up the some kind of projects. So here in the sector composition, when we talk about the sector composition, So at present, in 2020, almost 37 gigawatt of the power is coming from the wind, and 34 gigawatt of the power, not a percent, please, sorry. 37 gigawatt of the power is coming from the wind, and 34 gigawatt of the power is coming from the photovoltaic. So, but in next 5 years, they are estimating that the solar power will dominate the wind power. That means the solar power installation will overcome the wind power installation, because nowadays there are a lot of installation happening with the photovoltaic system. So here, biopower and small hydro also contributing around 10 odd gigawatt of the power in the renewable energy sector. So here the key trends, if you look at it, in every year, every financial year, the installation of renewable energy sources are increasing. Even the government also, they are come up with a lot of initiatives. You can say it's solar parks, hybrid wind PV systems, green energy corridor schemes are available. So with these schemes, they are promoting the renewable power generation in India. So when we come into that wind energy conversion system, just we are having the turbines. So there are two types of turbines. One is horizontal axis wind turbine and vertical axis wind turbines. So in earlier days, they have come up with the vertical axis wind turbines for mechanical applications. So for grinding the grains and for agriculture purpose, they have used this vertical axis wind turbine. But for power generation perspective, the horizontal axis wind turbine giving the higher energy capture in terms of energy efficiency, it looks good. So that's what nowadays just we can able to find a lot of horizontal axis wind turbines in the country, right? So when we come into that horizontal axis wind turbine, there are various components in it. So first we can discuss about the rotor components. So here rotor, just we are having the 3 blades, and these 3 blades will be connected in the hub, right? So here, when we talk about the number of blades, if you look at that, I hope all of you have seen the wind turbine. So the wind turbine having the 3 blades. So what's the reason? Is there any reason to have the 3 blades in that wind turbine? Anyone? Any participants? Any reason?
Dear participants, any of having doubt, please unmute your audio and directly interact with our resource person.
Yes. Okay. Here, when we look at that wind turbine, we are having the 3 blades. The reason is for mechanical stability issues. If you are coming with the 2 blades, what will happen at one particular condition? One blade on the bottom and another blade on the top. So the top blade will face the higher wind velocity and the lower blade face the lower wind velocity. The reason is behind this blade, you are having the tower. So that will give the shading effect. So once the top blade faces the higher wind velocity, then you'll get the mechanical stability issues. Even the 4 blade system also, at one particular point of time, one blade on that shading of this tower and another blade on the top. So here what will happen, just we'll get the mechanical stability issues. So that's what people always prefer, the odd number of blades in the horizontal axis wind turbine. So during the, if you're having the odd number of blades, so at any particular point of time, if this blade comes here, these 2 blades are in this direction. These 2 blades are in the direction, not exactly perpendicular to this blade, right? So that's what they will use, the odd number of blades in the system. So at the same time, the blades are tilted. It's not a flat blades. You can look at here, the blades are tilted. So why this blades are tilted means because of the aerodynamic properties. Then only can able to capture the energy from the wind, right? So that's what these are the blade characteristics. Then when we come into this naturally, so this part on the top, if you look at this top, this part will be called as naturally. So this naturally having the generators, gearboxes, and other associated electronic controllers, right? So in this naturally, just if you look at that, the rotor is connected to the low speed shaft and it's connected to the generator through the gearbox. Why we need to use gearbox means, if you look at the wind turbine, what is the rotational speed? Do you have any idea? So at what speed the turbine is rotating? As we electrical engineer, we normally used to say in RPM. So do you have any idea about how much RPM the wind turbine will rotate? Commercial wind turbines. So almost you can say it's 50 RPM, 50 to 70 RPM. So this 50 to 70 RPM is not enough to rotate your generator. Why? Because you can take the 4-pole machine for 50 Hz system, the synchronous speed is 1500 RPM. So that, this machine needs to operate as a generator means you have to rotate it at least in a synchronous speed or above the synchronous speed. So synchronous speed, I can say, is 1500 RPM. So that will be in the hundreds, a few hundreds of RPM. But here you are getting the speed in the few tens. So is it sufficient to connect directly this generator to the shaft? No, it's not possible, because if you're rotating at 50 RPM or 60 RPM, you cannot be able to generate the power. So to convert the low speed to high speed, just we are having the gearboxes. It's a simple example as we are having it in the motorcycles. The IC engine speed is huge, so your motorcycle speed is in some tens of kilometer per hour. So that is because of the your gearbox. Even if you look at the engine speed in your speedometer, it's in thousands of RPMs. But your speed in the vehicle is less. So the same way in the wind turbine also. That's what just we are using the gearboxes here, right? So next part is the generator. Just we are having the various types of generators. So we will discuss in the future slides how we can choose the different generators for the wind energy conversion system. So then when we come into that power electronic controller part, yes sir?
Excuse me, can you repeat once again, sir, what you said about gear? Sorry.
Yeah, gearbox, you can use it for speed conversion. So if I talk about the generator, so generator for a 50 Hz power supply system, we are having a 4-pole machine. So what is the synchronous speed of that machine? The synchronous speed is 1500 RPM. Am I right?
Yes, sir. Yes, sir.
So 1500 RPM. But here, if you look at the rotor speed of the wind turbine, the rotor speed of the wind turbine is in 50 RPM or 60 RPM.
Yes, sir.
So is it possible to directly connect this low speed shaft to the generator? It's not possible. If you are directly connecting it, it will operate at 50 RPM or 60 RPM. So that speed, we cannot be able to generate the power, right? So for that, we have, for converting the low speed to high speed, then you need to use the gearbox. As like our in the motorcycle, just we are having the gearbox in the motorcycle, right?
Okay.
So in the motorcycle, just we are depending on the speed, just we are changing the gear. Number of gears, right? So here we are not changing the gear, but here the speed variation is only very few hundred RPM. So here, the stage gearboxes we will use here.
Okay. Yeah. Accordingly, speed it automatically changes that rotation.
Yeah, it changes. If it's a 50 RPM, then just at least you can get 1,500. We can say 1,500 RPM. If it's a 60 RPM, then you may get 1,700 to 650 RPM at the high speed side.
Okay.
So here, just we can use various types of generators and topologies that we will discuss in the future slides. Then question mark here, why we need to use the power electronic converters? That's a very big question here. So why we need to use the power electronic converters means that we can discuss once you are discussing about the characteristics of the wind turbine. At time we can easily able to get to know why we need to use the power electronic converters in the wind turbines, right? So here, if you look at here, just we are using the anemometer and wind van. This anemometer and wind van will be used for measuring the wind speed as well as wind direction. So why we need to measure the wind direction means, I mean, the wind direction is not always one direction, even if we can realize it in our real life. So the direction of the wind will keep on change for every hours. So if you are fixing this wind turbine only in one phase, one direction, then you cannot able to capture the more energy from the wind turbines. So depending upon the wind direction, you have to rotate this entire naturally to face the wind, So then only you can able to capture the good energy from the wind, right? So here, if you are looking at here, in between your tower and then naturally you are having the yard drive. So this yard drive can be useful for rotating this entire system, entire naturally. So this yard drive, this wind van feedback is given to this yard drive. So this yard drive can rotate the entire naturally to face the wind, right? So this what here. Then when we come into the anemometer is used for measuring the wind velocity or wind speed. So during the gusty wind speed, means if you're during the storm, a windstorm, you'll get the highest wind speed. During that time, just you have to stall the wind turbine. When the wind speed is lesser than the cut-in speed, then you have to stop the wind turbine. So for that purpose, just you have to use the anemometers to measure the wind velocity. That wind velocity will give it as a feedback to your electronic system, right? So that and all we will discuss in the maximum power point tracking of the wind energy conversion system. So when we come into the cost perspective, the 20% of the cost will go to the rotor parts. So just you can say it's in a rotor part, you are having the blades, hubs, and everything. Then 35% of your cost goes to this gearbox, generator, and electronic controllers. So in this 35%, the high you need to spend a lot of amount to the gearbox. The gearbox cost is very much costlier in wind turbine. So that's what nowadays people are working on, gearless wind turbines. So gearless wind turbine are also manufactured by the different companies. So let me put one more question to the audience. Do you know any idea about what are the companies is available in the wind turbine manufacturing?
Siemens is there.
Sorry, Siemens? Yeah.
Siemens.
Oh yeah, exactly. Siemens and even Reliance also, they are having their own subsidiary company. It's a region. And you are having the Vestas. So Vestas is a Danish company that also is available in India. And one Indian company. So making program.
Suzlon.
Yeah, Suzlon, exactly. Suzlon is there. Suzlon is the Indian company. So they are manufacturing the wind turbines in-house. In-house means in India itself. That's an Indian company. Right? Okay. So these are the companies, they are manufacturing the wind turbines. So nowadays they are focusing on the gearless wind turbines to reduce the cost of the system. And structural, when we come into the structure of the wind turbines, it takes almost 15% of the total cost. Even you can say it's a tower, yaw control and all, it comes under this structural components side. Yeah. Now we will go to the little bit of turbine side. Then once you understand the turbine, then it will be easy for you to select the generator or topologies, or you can say it's the power electronic topologies. For that, first we have to understand, as electrical engineer, we will worry about only the electrical output, right? Electrical output from the generator. Even the generator also we can, people are working. So now for a generator, we need to give a mechanical power as an input. So this mechanical power is coming from the wind turbine. So how we are getting the mechanical power output from the wind turbine, once you can understand, then it will be very easy for you to control your turbine. So the mechanical power is the output of the turbine. So that we can say of rho AV cube Cp, of rho AV cube Cp. So how we are getting this mechanical power means, just we can derive from the energy, kinetic energy available in the wind. So that from that kinetic energy, you can derive this mechanical power output. So this mechanical power output, once you are working on the wind turbines, you must know about this expression. So this is the mechanical output of the turbine, that is of rho AV cube Cp. So here the rho is the air density, and A is the area, V is the wind velocity, and Cp is the power coefficient. So here in the power coefficient, just we are having that, this will be depending upon the tip speed ratio and bits limit. So bits limit, you can say it's a bits limit, it's a 0.59. That's the maximum value of this bits limit. So 0.59 is the bits limit. So whenever we are talking about the conversion efficiency of the wind turbine, the maximum conversion efficiency of the wind turbine is 59%, right? So 59% is the maximum power conversion efficiency of the turbine. So when we come into the photovoltaic panels, the conversion efficiency is 18%, right? So here it's a 59% conversion efficiency. So that limits the bits limit limits the efficiency of the wind turbine, right? That's part of the Cp, power coefficient. Okay, now other three parameters also there. Another is rho. Rho is the air density, right? So this air density depending upon the location or depending upon the environment. So the air density is desired. You cannot able to decide it. That's a location specific, right? That's not in your hand. That's in the particular area side. And so we cannot able to control the air density. Am I right? Then next one is area. So what is the area means? If you look at here, just we are having the three blades. So this tip of that blades, if you join, you will get the circle. So this will be called as a rotor area. This will be called as a rotor area. So this rotor area will be depending upon the which parameter. So if I join this tip of this plates, then I can get the circle. So once you are increasing the area, your power output also will increase. Mechanical power output also will increase. So if I want to increase the area, what I need to do? How you can increase that area? By increasing the length of the blade. Once you are increasing the length of the blade, then area also will increase. Once you increase the area, then your turbine power output also will increase, right? Because it's a power output is proportional to the area, right? So then area. So that area is in the manufacturer side. Once you manufacture the blades, that also area also will be fixed. So area also will be fixed. Then this air density is on the location specific. The Cp is already fixed. So which one you can able to vary? You cannot able to vary. So your power output of the turbine, once you are install the commercial wind turbine, the power output of the turbine is directly proportional to the cube of the wind speed. So cube of the wind speed. Even if you are changing the 1 meter per second in the wind velocity, that will impact huge in the power output of the turbine. So that's what we can say. The power output of the turbine is directly proportional to cube of the wind speed, right? So by using this equation, by using this power output equation, just we can plot the characteristics of the wind turbine. We will see in the next slide how we can use that equation for drawing the power characteristics of the wind turbine. So in y-axis, you are having the mechanical power output. In x-axis, you are having the wind turbine speed. Please note it down. In x-axis, wind turbine speed. In y-axis, you are having the power output. So just we can take that equation, and for one particular wind velocity, you can take the one particular wind velocity. I can say, here every unit, sorry, per unit. So just I will take the 0.5 per unit wind velocity. You can take one wind velocity, and you can substitute in that equation with a different wind turbine speed. Then I'll get this curve, right? I'll get this curve. Then for next case, just we can substitute the 0.6 wind velocity. This curve is for wind velocity of 0.6 per 0.6 per unit. So in that case, for a different wind turbine speed, if you are calculating then you'll get the second curve. This is the second curve. For 0.7 per unit wind velocity, you can vary the wind turbine speed, and you can plot the PM. So you'll get this curve. For 0.8 per unit wind velocity, you'll get this curve. Up to 1 per unit, you can substitute by varying the wind turbine speed. You will get the mechanical output power curve as like this. Am I right? So what it means that, so for example, I can take the wind velocity in a real time. The wind velocity will keep on change, right? Your wind velocity will keep on change. But for a particular wind velocity, I have considered, and just I'm analyzing that curve. So here, if you look at it, 0.9 per unit wind velocity. For my study purpose, I consider that my wind velocity is 0.9 per unit. So if your wind velocity is 0.9 per unit, then that time your turbine is rotating. This is the turbine speed, right? The x-axis is turbine speed. At that 0.9 per unit wind velocity, my turbine is rotating at this speed, 1.2 per unit speed, right? At the time of wind velocity of 0.9 per unit, your turbine is rotating at 1.2 per unit. So what's the output power? You will get it from the turbine. At this point, you are able to see my cursor, right? Audience, please.
Yes, sir. It's your cursor is visible.
Okay then. So if my wind velocity is 0.9 per unit, that time I'm operating my turbine. The turbine speed is 1.2 per unit. So what's my output power? Mechanical power output power? It's a 0.5 per unit, right? This is the point, right? 0.5 per unit. So that time, for say wind velocity is same, just we can consider that my turbine is operating at another speed. My turbine is operating at 0.6 per unit. So if we are operating at 0.6 per unit, then what is your output power? Again, it's a 0.5. 0.5. Again, it's a 0.5. Instead of operating my turbine in this speed and this speed, I'm operating at this speed. So this speed, what is this speed? It's a 0.9 per unit. So I'm forcing my turbine. So if I get this 0.9 wind velocity, because we are having the anemometer. So from the anemometer, you can get to know what's your wind velocity. So at that wind velocity, you are forcing your turbine to rotate at 0.9 per unit. 0.9 per unit. If you are rotating your turbine at 0.9 per unit, so what's my output power? My output power is 0.7 per unit, right? 0.7 per unit. So as a engineer, in which point you will try to operate? This point or this point, 1.2 per unit wind turbine speed, or 0.9 per unit wind turbine speed, or 0.6 per unit wind turbine speed. So just we have to operate at this point, right? 0.9 per unit wind turbine, 0.9 per unit speed. So then only I am getting the maximum power output from the wind turbine. That is a 0.7 per unit. If I am operating here or here, my output power is 0.5. So if the wind velocity is same. In all three cases, wind velocity is same. So just the turbine speed is different. So as an engineer, we have to force the wind turbine to rotate at 0.9 per unit to get the maximum power output from the turbine. So that's a 0.7 per unit. So always I force the turbine to rotate at this point, so that my output power from the turbine is higher, right? So this point will be called as maximum power point. This point will be called as maximum power point, because at this wind velocity only you will get the maximum power from this point. So for each wind velocity, you are having the 1 point. So in between, just we have taken the value 0.5, 0.6, 0.7 like this with a 0.1 difference. If you are taking the 0.5 difference, what will happen? You will get another curve in this. So even 0.2 or 0.3, you will get the 4 or 5 curve in between these two curves, right? So that means that the resolution you can change, right? So, but in a real time, it's just you will get many points in this region. But here, if you are joining this all maximum power points, you will get the curve like this. You will get the curve like this, right? So this is the maximum power points for all the wind velocities. So here, what is the thing you understand? So whatever the wind velocity, we have to force the turbine to rotate at that speed, right? Then only you can able to, you can operate your machine at this point. So for that, how can I adjust the speed of the wind turbine? How can I adjust the speed of the wind turbine? Is it possible to change the speed of the wind turbine? Yes? Any idea? Okay, I'll tell you. So there are two types of control.
Sir Vijayakumar, sir, I think that Dilip say something. Mr. Dilip, unmute your audio and tell them.
I cannot able to.
No, sir. No, I didn't.
Okay. Okay, sir. No issue. Okay. So here, just you have to change the speed of the wind turbine. How we can change the speed of the wind turbine means one is the mechanical control and another one is electrical control. In mechanical control means just we can change the tilt angle, because just I as already told you, if you are changing the angle of the blades, the aerodynamic characteristics of the turbine will change. So that will not face the wind speed, so that you can able to change the speed of the wind turbine. That means it's a mechanical control. Just we are changing the tilt angle of the blades by for changing the aerodynamic characteristic. So that's a one way. That will be called as a pitch control. But normally we won't use this mechanical control for changing the speed of the wind turbine. Why? Because the inertia, because the wind turbines in thousands of tons, right? So it's not exactly thousands of tons. You can say it's hundreds of tons. So you'll have the high inertia. So the response time will be less. So if my wind velocity is 0.9 per unit, 0.9 per unit. If I want to change that speed to that 0.9, then I have to change the tilt angle. So tilt angle means just we have to rotate the blade. For changing the angle of the blade itself, it will take the 5 to 10 minutes. Then that time your wind velocity will change, right? So after 5 to 10 minutes. So that time, your response is slower. So that's what they will not use pitch angle control for implementing the maximum power point tracking. The best option is electrical control. How they are using electrical control means in a shaft, what you are connecting, just you are having the low speed shaft and high speed shaft. In your high speed shaft, just we are having the generator, right? So here, if you look at that, if here, if I'm changing the generator speed, right? So I'm changing the generator speed. So how you are changing the generator speed? I mean, if you are changing the generator speed, what will happen? That speed will reflect into the turbine speed. If I change the speed of the generator, then here also the speed will change. Am I right? So how we can vary the generator speed? It's our electrical drives. So just we are having an electrical drive subject, an electrical drive speed control of the motor. So how we can control the speed of the motor? Just we can connect the power electronic converters. Without power electronic converters, it's very tough to change the speed of the machine. So connect the power electronic converter. Then you can use scalar control or vector control for controlling the speed of the machine. So once you are controlling the speed of the machine, then turbine speed will change. It's an indirect control, or you can say it's an electrical control. This control is speed because in a power electronic converter, just we are having the frequency in a kilohertz. So that will be having the quick response. Quickly it will change the speed of this machine. So that will be reflected in your wind turbine speed, right? So this is the electrical control. Normally they will use the electrical control for implementing the maximum power point tracking, right? So now you can understand what is the requirement of power electronic converters in wind turbines, right? So if you want to implement the maximum power point tracking, obviously you have to use the power converters, right? So just we can use the power converters to get these points, right? So from this, just we are having the power, this will be called as a power characteristics, power versus wind velocity, you can plot it. So here, this is the cut-in speed. So you have to start your turbine, at cut-in speed and above. So if you're operating below cut-in speed, then whatever the power generated from the generator, that will be enough to compensate your losses. So that's what normally they won't operate below cut-in speed. So they will start the turbine at cut-in speed, then they will go up to rated speed. So this rated speed, if you look at it, up to cut-in speed to rated speed, you can implement the maximum power point tracking. So this is the region you will implement the maximum power point tracking, right? So here, what control you will use? You will use the generator. You will use to control the speed of the turbine, right? This is the MPPT region. From cut-in speed to rated speed, this is the MPPT region. So in rated speed, you will get the rated speed means rated wind velocity. So normally typically the cut-in wind speed is 3 meters per second to 5 meters per second. 3 meters per second to 5 meters per second. Then at 15 meters per second, 15 meters per second to 18 meters per second, your turbine able to generate the rated power. Rated power, I am using a 5 megawatt turbine means at 15 to 16 meters per second of wind velocity, you can able to generate the rated power, 5 megawatt. So after this rated, once it's reached the rated power, then whatever the wind velocity, even if your wind velocity is 20 or 22, then your power output of the turbine is constant because that's a that's a capacity of your rating of your turbine. So once the wind velocity increases above rated speed, above rated wind velocity, then your power output is constant. So that's what here the power output is constant. So here they will use the pitch angle control to control the speed of the turbine because here if I say it's a 15 meters per second to 25 meters per second is the cutout speed. So in this region you can use the pitch control. So because here the power output is constant, even your response is slower, it doesn't matter, right? So that's what they will use the pitch control to control the turbine. So cutout speed, after cutout speed, normally they'll stall the turbine. Stall the turbine means they stop the turbine to rotate. Why? Because during the high wind speed, it leads to damage your turbine. So that's what cutout speed, once it reaches the cutout speed, 25 meters per second, that time they will stall the turbine. So that's after that, that's a parking, right? So this is the power characteristics of your wind turbine. So once you understand these characteristics of the wind turbine, then that will be easy for you to select the converter topologies as well as generator types, right? So any clarification on this power characteristics? Once you understand, now we can get to know that why we are using the power electronic converters in wind turbines, right? So power electronic converters are used to control the speed of the machine. Why we are controlling the speed of the machine? To control the speed of the turbine to reach that maximum power point, right? So that's what just we are using the power electronic converters in wind turbines. Any clarifications on this topic? You're not. Any questions? Yes. Okay. If you are not having any questions, I will move forward. So next, wind energy just we have discussed about the various components in the wind turbines. Now we are going to talk about the wind energy conversion system. We are talking about the entire system. So here, when we talk about the wind energy conversion system, you can classify as grid connected system or standalone system. The same applicable for photovoltaics also. In a PV system also, you are having a grid connected system, standalone system, right? So here in a grid connected system, you are generating the power in the one place and you are injecting to the grid, so that can be utilized in anywhere in the net. You are generating the power at local and you are supplying your loads. Whether if I'm using it in my home, then I can supply that power to my gadgets in my home. So if you are in the institute, just you can generate the power and you are supplying your institute loads or any commercial buildings, right? So here, what are the control parameters you have to consider in grid connected system and standalone system? In grid connected system, so what are the control parameters? Because it's connected to the grid. So what are the control parameters I have to look into it? In terms of DG, I can do active and reactive power control. So whatever the grid connected papers you have read, whether it's a photovoltaic or wind, they may discuss about the active and reactive power control. So these are the two parameters in the grid connected system. So once if you are having the active and reactive power control, then you can able to compatible with the grid codes of the country. So for every country, we are having the grid codes. If you want to support grid codes, then you should have the active and reactive power control. So one is this active and reactive. If you are taking any photovoltaic, grid connected photovoltaic system or grid connected wind system, they will discuss about active and reactive power control. One is this perspective. Another perspective, they will discuss about grid synchronization. Because in lab already we know if you are having the synchronous generator, then we use dark lamp method or synchronoscope method for synchronization. So here also, if you are having the inverter, any source, if you want to synchronize with the grid, then there are a lot of grid synchronization algorithms available, right? So in that, they may work on phase lock loops. This is the second perspective. Then third perspective, power quality issues. Whether it's a wind or photovoltaic, it's always give the disturbance to the network. Why? Because these two sources are intermittent one, right? So because of that intermittency, this will create a lot of problems in the grid, power quality issues. So for mitigating this power quality problems, people will work on different aspects. They may put StatCom, they may put anti-active filters, and all they may work on the distributed generation side, right? Distribution network side, right? So another thing, in the grid connected system, they may work on the different power converter topologies, right? Different power converter topologies, they will work and they will propose some new converter topologies for improving the performance of the system. So these are the 4-5 aspects they will work on the grid connected PV system or grid connected wind systems. So when we come into the standalone systems, what are the control parameters in the standalone system? As I'm having a load in my home, I'm having my gadgets or home appliances. So what's my expectation from the utility? Anyone? What's my expectation?
Constant power.
Constant power. Is it the power, because my load is different equivalent resistance value. So is it possible to expect the constant power?
Not possible, but we need like what I'm saying, constant voltage. There should not be any flexion.
Exactly. Yeah, constant and I mean power and voltage, there is huge difference. So power, I cannot fix it because my loads will keep on change. So you cannot expect the constant power. Then you have to, I mean, you may expect constant voltage and constant frequency, right? Constant voltage and constant frequency. So this is my expectation from the source. So if I'm supplying, suppose if you are designing the standalone system with the help of wind and photovoltaic, then you have to supply the constant voltage and constant frequency. So here, if you are working on standalone system, you have to focus on voltage regulation and frequency regulation, right? Voltage regulation and frequency regulation. So here, I mean, if you look at the research perspective in the standalone wind and photovoltaic system, so here the wind and photovoltaics are intermittent one. Am I right? It will keep on change. It's not in your hand. It's on the nature's hand. So this irradiance and wind velocity will keep on change. At the same time, if you are connecting that to your loads, like my home. So in my home, I'm having the 4 rooms. Even in each room, my load demand is not constant, right? Sometimes I may switch on the AC. In some room, I may switch on the bulbs and switch off the refrigerator, or switch off my oven, or switch off my. What I want to convey here is you are not maintaining the constant load at the load side. So the load will keep on change, because that will be in the consumer side. The consumer will keep on change the loads. The load pattern also, it's not constant. So is it possible to match this supply and demand? Is it possible to match the supply? I mean, even your supply also, it's a oscillatory one. Your demand, load also, it's an oscillatory one. So how we can match this? It's not possible to match, right? So this is the power balance. So in a renewable energy system, for supplying the standalone loads, you never ever match the load with the supply, right? Sometimes supply will be more, load will be less. Sometimes the load will be higher, supply will be lower, right? So what is the solution for that, for the power balance?
Sir, Sir, if you need, we'll take for 5 to 10 minutes break. After then we'll start them. It will be only.
I'm okay that. If admins are okay, then I'm okay with that.
Okay, you continue, sir.
Okay.
Thank you, sir.
So what's the how I can match that supply and demand in a standalone system? This when you are designing the power supply, then you have to think of it, right? So sometimes my load will be higher, but supply, I may not get the irradiance or wind velocity. So how can I compensate my loads?
I think storage device we can.
Yeah, exactly. We can integrate the energy storage devices in it. So once you are integrating the energy storage, when you are having the excess power, if your load demand is less than your supply, that time the excess power can be used to charge your batteries. Then whenever your demand is more as compared to the source, irradiance or wind velocity, the excess power can be, the deficient power can be supplied from the battery. So we can discharge the battery. Not like in our country, in India, once if the demand is more, okay, switch off, you can isolate the feeder, then we won't get the power supply for 3 to 4 hours. That's what we experienced during the power holidays, right? In the last 4 to 5 years back, we have experienced that kind of power cuts, right? They may say it's a power holidays. So per day you may not have the power for 3 to 4 hours, right? So even Tamil Nadu, we have experienced 8 hours power cut also per day, right? So that kind of non-reliable things you cannot your supply systems will not be provided to your load. So whatever the system you are designing for standalone system, then you have to give the continuous power and reliable power to the consumers, right? So that's what it's that's what when you are designing the standalone system, people may talk about this power balance by incorporating the energy storage devices into that. Then they will ensure the reliable supply to your loads. One perspective, they will work on this perspective, and constant. You have to maintain the constant voltage and frequency. So voltage regulation and current regulation, they will propose different control strategies in the standalone systems. And again, people may talk about a standalone system grid. If you are talking about the microgrids, so just your distributed, wind PV can supply the power to the microgrids. If any fault happen in the microgrids, that should be islanded, and he has to supply the critical loads. So that islanding technique also they will use. So that means between these two types, once it's a grid connected system, that's in the microgrid, it's connected to your microgrid, that will give the power and operate it. Once there's any fault in the microgrid, then this grid connected system will be isolated and supply it will become a standalone system to supply the voltage and frequency constant at the load sides. Right. So these are the perspectives. These are the areas people are working in the research. Even you can take any standalone system, they will work on this voltage regulation, frequency regulation, or they will work on this power balance, energy management system by integrating the energy storage devices. And another perspective is topology side. We can propose different power converter topologies between your source and load. So people are in the power electronic perspective, they may work on that areas. So these are the research areas in the grid connected system and standalone system. Now, if you are a research scholar or if you are a researcher, you have to decide in which area you have to work on it. First, that you have to decide whether you have to work on standalone system or grid connected system or in a microgrid system. So that's up to you. All right. Okay. So now we'll go into the main components of wind energy conversion system. So here just we can divide mechanical power components and electrical power components. So in a mechanical power components, just we are having the rotor, gearboxes, and generator. So here I have mentioned this rotor can be used for power conversion and control. Why? Because just we are using this rotor for, excuse me. Yeah, this rotor can be used for converting the kinetic energy from the wind to mechanical power, right? So that's what I can say is a power conversion. Control. By changing the tilt angle of the blade, right? By changing the tilt angle of the blade, I can able to control the speed of the turbine, right? So that's what I mentioned, power conversion and control. Then this will be transmitted to the power, whatever the power, mechanical power, that will be transmitted to the generator through the gearbox. So gearbox is used for transmission, power transmission, right? So here, please note it down. I mentioned gearbox is optional. Why this is optional means, even nowadays people are come up with the gearless wind turbines to improve the cost of the system, so that they can able to reduce the total cost of the wind turbine by eliminating this gearbox. So that's what I put. Types of generators we'll discuss in the next slides. And this can be used to power conversion, mechanical power to electrical power. And by controlling the speed of the machine, you can able to implement the maximum power point tracking. So that's what I put the control on. So here the power converters. So here the power converters, again, it's optional. Once if you want to implement the maximum power point tracking, then you can go with the power converters. But in 1990s up to 2005-8, people are installed the wind turbines without the power converters. That wind turbines are called fixed speed wind turbines. That we will discuss in the next slides, right? So that they will not use these power converters. So that's what I put optional. So here gearbox, here power converters are optional, right? So here I'm using the power transformer between the wind turbine and the grid. So what's the purpose of this power transformer? To match up the voltage, right? If my incoming voltage will be a 110 volt, if my grid voltage is 220, then I have to match with this grid voltage. One is that purpose. And another important application of this power transformer is it will provide the isolation. So once if you are having the electrical isolation, whatever the fault it happened in the grid, that will not be transmitted to your wind turbine. Or if any fault in the wind turbine, that will not be transmitted to your network, so that you can able to save the blockouts, right? So these are the different components in the wind energy conversion system. So wind turbine concept. So when we come into the wind turbine concept, there are you can say it's two types. One is a fixed speed wind turbine, and another one is variable speed wind turbine. I'll come to you one by one. So earlier days, up to 2005, the fixed speed wind turbines are very familiar. And even whatever the turbines installed, wind turbines installed before 2005, even nowadays also fixed speed wind turbines, they are installing it. And all the turbines before 2005, maximum turbines are based on fixed speed wind turbines concept. So here the fixed speed wind turbine concept will have the gearbox in it, but it won't have the power electronic converters. Because in 2005, 2000 and all, it's not that much mature power electronic technology we have. Even if you want to have the megawatt level of converters, if any simple fault happen, your entire system will be isolated, and even the wind turbine owners face the able to only sometimes they may stall the turbine for a long days for maintenance if they won't get the maintenance people to take the repair of the converters and all. So that time they use the wind turbines without power electronic converters. So if you are saying there is no power electronic converters, then there is no maximum power point tracking, right? So here you cannot implement the maximum power point tracking in the fixed speed wind turbines. So because of that, the energy output, if you are calculating the energy output of the turbine for a year, then that is the limited one. So here, normally they will use the screw cage induction machines. So already we know the screw cage induction machines. So we have done a lot of experiments on that. So the same machine can be used as a generator. Induction machine can be, screw cage induction machine can be used as a generator in this fixed speed wind turbine, right? So when we come into the variable speed wind turbines, is a very modern technology, you can say. So just we are having the converters, just we are incorporating the power converters with that. So by having the power converters, you can able to incorporate the maximum power point tracking. So here just we are operating the machine at variable speed, right? So here the machine, you can say wind turbine is operating at fixed speed. Fixed speed means not exactly the constant speed. So in a screw cage machine, you are having the slip ranges. So what is the slip range of the induction motor? If you are operating as a motor, then 1004, at no load, you are getting the 1480 RPM for 4-pole and 4-pole machine, 50 Hertz system. So for if you load that machine at full load, it may be 1400 RPM, right? So you can say it's a 10 to 20% slip range, right? So that's for small machines. So if you are taking the megawatt range, the slip range will be in the 2 to 3%. 2 to 3% is the slip range in the large machines. So these machines can be used. So 2 to 3% slip range only it will operate. So above 1500 RPM, it will act as a generator. So up to 1490 RPM, the generator generate the power. So that time only 90 RPM variation. So that 90 RPM will be considered as a negligible. So that's what we call it as a fixed speed wind turbine. So here it's not like that. So we can able to operate that generator from 1500 to 1800 RPM, right? Or even below that also you can make that generator to generate the power. We'll discuss in the future slides. So that's what it will be called as a variable speed wind turbines. So here it's possible to implement the maximum power point tracking. So when you are calculating the energy output from this variable speed wind turbines, it's highly competitive with the fixed speed wind turbine. That means the energy capture is higher with the variable speed wind turbines. Here, normally just we'll use permanent magnet synchronous generator, doubly fed induction generators, and wound rotor induction generators, PMSG, permanent magnet synchronous generator, doubly fed induction generator, WRIGs. So in here we will use permanent magnet synchronous machine. In DFIG and WRIG, we will use the slip ring induction machines. So when we come into the fixed speed generators, normally in the wind turbine we won't use synchronous generator. The reason is, if you want to generate the power from the synchronous generator, you have to operate at a constant speed. If it's a 4-pole machine, 50 hertz system, 50 hertz supply system, then always you have to rotate at 1500 RPM, right? You have to operate at the constant speed. So, but in a wind, it's not possible, right? At least you will get 100 RPM difference. So that's what you cannot use this machine as a generator. And another disadvantage is just you are having the armature as well as field. So two types of supplies. One is, armature, you will get the AC supply. In the field, you have to energize with the DC supply. So you require the separate DC supply. Even the wind turbines are located in the remote areas. So the maintenance is a huge problem. Then in addition to that, synchronization. So synchronization, just you have to use dark lamp method or synchronoscope. Then if you're using the synchronous machine, always the synchronization is used there, right? So because of these three reasons, we won't use this synchronous machines for wind turbine application. Next one is spool cage induction generators. Yeah, a normal spool cage machines. So when you are connecting these spool cage machines to the grid, then it will act as a motor, right? Just it will rotate at no speed, no load speed, no load condition. You can say for 4-pole machine, 50 hertz supply system, it may rotate at 1480 RPM. Am I right? 1480 RPM. That is in the clockwise direction. You can consider the clockwise direction. So if you are having, here you are having the prime mover, that's a wind turbine. So from the wind turbine, you will get the power that can able to rotate in the same direction, above synchronous speed. Now it's operating at 1480 RPM. So if my prime mover able to rotate this machine above 1500 RPM, 1500 RPM or above 1500 RPM, then this machine will act as a generator, right? This machine will act as a generator. That time the slip will be negative, right? So once you are rotating this machine above 1500 RPM, or you can say above, so that time if you look at the current direction will be reversed. So earlier in the machine operation, it takes the current from the grid and it will operate as a motor. So once you are operating as a generator, then the current will be reversed. But when you are calculating the powers, active and reactive power, so this machine always takes the reactive power from the grid, whether it's act as a motor or generator. So always it draws the reactive power from the grid. That means it draws the magnetizing current from the grid to create the flux, right? So that's what, whether the induction machine operate as a motor or generator, the power factor at this point is lagging. So always it's operated at the lagging power factor operation. So for that, if your lagging power factor operation means you're drawing the reactive power from the grid. You're drawing the reactive power from the grid, right? If you're drawing the reactive power from the grid, then just you will get the power quality issues at the network. So at the point of common coupling, just you have to connect the capacitors. So these capacitors will provide the reactive power compensation, so that at the point of common coupling, you can able to maintain the unity power factor. So whatever the magnetizing current required by this generator is supplied by the capacitor bands. So from the grid, you are not taking any magnetizing current, right? So here there is no synchronization issues, and only the disadvantage is lagging power factor operation. That can be resolved by connecting the various capacitor banks, or you can say nowadays there are a lot of fax controllers are available like StatCom and all. By connecting that, you can smoothly able to vary the reactive power at the point of contact plane, right? So this is the generator topology. It's available in the fixed speed wind turbines. Even it's very famous. Even nowadays, if you are calculating calculating the total installed capacity, 80% of the power is generated from this base. Spool gauge based wind turbines, spool gauge induction machine based wind turbines. That's called wind turbines. So here you cannot able to implement the maximum power point tracking because you are not having any power electronic converters in this, right? So the same spool gauge machine, you can use it for supplying the standalone loads. So as I already told you, the wind is intermittent one, the loads also it's an intermittent one, right? You cannot able to match the supply and demand. So, but however, before going to the matching the supply and demand, we have to look at the basic operation of this self-excited induction generator. So without the capacitor, if you are connecting only the load to the spool gauge induction machine, this machine will not supply your loads. Even if you are operating the machine above synchronous speed, it will not you will not getting any voltage at the terminals. Why? Because as I already told you, spool gauge machines require the magnetizing current from the grid. So here there is no grid available, there is no source available to provide the magnetizing current. So that's what this machine will not induce any voltage here. So for that, just we can come up with this topology. You can connect the shunt capacitors. You can connect the capacitors at these terminals. So these capacitors will provide the magnetizing current to the machine, so that you will get the induced voltage and frequency at the started terminals. But what are the voltage and frequency? What are the, because they are not matching the load and source. So I can say that terminal voltage and frequency is not constant. So we can use this for frequency insensitive loads. Frequency insensitive loads means it's a resistive loads, like a heating loads. You can use this power. So what I can say here is the voltage and frequency depending upon all the parameters, load parameter, because load is keep on changing. It depending upon the load parameters, depending upon the capacitor value, depending upon the load, you can say wind speed and the generator parameters. So we cannot come up with the optimum points of this. Even you can put some optimization techniques to optimize this. Even if you optimize this, then the voltage and frequency is a variable one. So for that, we have to connect some energy storage device with the DC. Some power electronic converters. That time it's possible to maintain the constant voltage and frequency. Next, when we coming to that variable speed turbines. In a variable speed turbines, there are different topologies. So now I'll take some 2 minutes break. Just you can, if you have any questions, you can ask. Please, you can accumulate the question and you can post to me up to this slide. If you are having any questions, I'll be happy to answer. So now I'll take 2 minutes break and I'll come back. Any questions in between?
Dear participants, if you have any questions, you can unmute and you can ask.
Sir, what's the time?
Sir, 3:30, sir, till 3:30.
3:30, sir.
3:30, sir?
Yes, sir.
Okay, sure. 2 hours, right?
2 hours, sir.
Okay. Yeah, if any questions, I'll answer that. So.
Dear participants, you can unmute your mic and ask if you have any queries. Sir, I'll just get 5 minutes break, sir.
Yeah, sure, sir.
Okay, sir.
Oh.
Dear participants, the session will continue at 3:10 p.m. Okay, having a 3 to 5 minutes break.
Yeah, shall we start, sir?
Yeah, yes, sir. Yes.
Yeah. Now, just when we come into the variable speed wind turbines, in variable speed wind turbines, there are 4 topologies normally we are using. So one is permanent magnet synchronous generators, and again we are using the spool cage induction generators also for variable speed turbines. So how means I'll tell you how we are using this spool cage machine also for variable speed wind turbines. So here, if you look at it, earlier case in the fixed speed wind turbines, there is no power electronic converters. But here, you are connecting the power electronic converters in between your generator and the grid. So these back-to-back converters are bidirectional converters. So whatever the magnetism current required by this spool cage machine is supplied by this rotor side converter because of the bidirectional nature. So once you are using the bidirectional converters, you need not to connect the capacitors here. So otherwise, if you are using the diode bridge rectifier, I can consider just I'm using the diode bridge rectifier here. So whether this machine will act as a generator, if you are using the diode bridge rectifier without any capacitors, no. Why? Because
No, sir.
yes, it's a diode bridge rectifier is a unidirectional one, so that will not provide the magnetism current to the machine. So if you are using the diode bridge rectifier, then you have to connect the capacitor banks here. If you are connecting capacitor banks, that capacitor banks will provide the magnetism current to the machine, right? So here it's a bidirectional converter, so you need not to use any kind of capacitors. So here just we are using the back-to-back converter. So here when we come into the permanent magnet synchronous generator, so already just we are having the permanent magnets in the field. So depending upon the wind velocity, you will get the variable voltage and variable frequency at the starter terminals, right? Variable voltage and variable frequency at the starter terminals. So here also just we are using a back-to-back converter. So that variable voltage, variable frequency, you can convert into variable voltage DC. Then that can be converted into that can be fed into the grid by using the grid type inverter. The same way here, it will take the magnetizing current from this converter and it can give the variable voltage and variable frequency depending upon this wind velocity. But here, please note it down. This will act as a generator even below 1500 RPM also. So how it possible? Because we are having the rotor side converter by varying the frequency. Because here you are using the converter. So if it's a grid means frequency is 50 hertz. So for 4-pole meson, 1500 is RP. 1500 is the synchronous speed, right? But here you are having the converter. So here by changing the switching angle of this converter, you can able to change the frequency at the starter terminals. If your frequency is 40 hertz, then what will happen? Your synchronous speed will come down. So in slow speed also, you can able to generate the even 1000. If you are increasing 40 hertz, so what is your synchronous speed? 120 f by p, right? For 4-pole, cancel 10. So just we are getting a 1200 RPM. 1200 RPM is a synchronous speed. So 1200, if you are able to rotate this meson in low wind speed with 1200 RPM, that itself will act as a generator, right? In a low frequency also, you can able to generate the power from these topologies. So here, if you look at it, this is the basic principal operation of this PMSG and SEIG in the variable speed wind turbines. So here we will analyze this system. So when we come to the analysis part, here just if you look at the converter ratings, these converter ratings must be equal to the meson rating, or more than the meson rating. So in this PMSG topology, this converter rating must be equal to the meson rating. So equal to the meson rating, why it's equal to meson rating means whatever the power it's generated from this generator, that can be channeled through your converter to the grid, right? So your converter must able to handle the power generated by this generator. So that's what the converter rating is equal to the meson rating. And here, yeah, we can able to control the active and reactive power independently in this topology. And the synchronization problem, obviously you will have the synchronization problem, but here you are using the grid type PWM inverter. By having the phase lock loops, you can able to synchronize with the grid, right? Next, school cage induction generators. So in the school cage induction generators, your power converter ratings, this power converter ratings must be more than the meson rating. Why means this converter only giving the magnetizing current to the meson. So this converter, if you are calculating the MVA, the MVA rating should be higher than this school cage induction meson, right? So that's what slightly, it's not much. I can say so 120% rating of your meson, right? So here also active and reactive power control possible. Grid synchronization issues that can be handled by the PLLs. So this is the case of PMSG and SEIG. So now we'll move into the slip ring induction mesons. So with this slip ring induction meson, you can propose wound rotor induction generator and doubly fed induction generators. So here, if you are using the diode bridge rectifier chopper along with the resistor, that will be called as a WRIG, wound rotor induction generator. Normally, you can say it's a rotor resistance control method, right? Rotor resistance control method for speed control of your electrical drive. The same topology, you can use it for wind turbine application also. But here, in a rotor resistance control method, this will take the power from the grid and operate as a meson. So then by varying the resistance, you are controlling the speed of the machine in the drives, right? How you are varying the resistance means just by varying the duty ratio of the chopper. By varying the duty ratio of the chopper, the equivalent resistance will change in the rotor windings, so that we can able to control the speed of the generator, right? So here the same topology you can use it for wind turbine application, but here just we are giving an input power on the shaft. So that means you are rotating above 1500 rpm, then it will act as a generator. So that time if you are changing the rotor resistance by varying the duty ratio, you can able to change the speed of the machine. So this can be utilized for implementing the maximum power point tracking in the variable speed wind turbine. So here also in top two topologies also, in rotor side converter, you are implementing the maximum power point tracking. That means just you can able, by varying the duty ratio of this modulation index of this rotor side, machine side converters, you can able to control the speed of the machines, right? That also is possible here. So here, by varying the chopper, by varying the duty ratio of the chopper, you are varying the rotor resistance, and you are controlling the speed. So this machine, this topology will operate above 1500 rpm, right? Above synchronous speed. And here the only one switch is there, only one power electronic. The chopper, they are having only one control device. So by controlling the only one device, it's very easy as compared to this. Here, just you are using the 12 controlled switches, 12 MOSFETs or 12 IGBTs. But here you can use only one MOSFET, right, or IGBT, depending upon the switching frequency, right? So that the control is very easy here, right? With the single switch. At the same time, the converters. So whatever the converters you are connecting at the rotor side, the converter ratings are 30%. Why the converter ratings are 30%? As compared to the top two topology. In the top two topologies, the converter ratings are equal to machine rating. If it's a 1 megawatt machine, then at least you have to use 1 MVA or 1.2 MVA converter rating. So, but here for 1 megawatt machine, you can use 300 kilowatt power rating of the converter. What's the reason? Do you have any reason? Because already you know the basic operation of slipping machines, right? So here in the rotor terminals, you are handling only the slip power. So slip power is, I said maximum slip is 20%. So 20% into PS. So 20% of the power you are handling at the rotor winding. So that's what the converter rating also, it's a 30%. So think of it. There is a 1 MVA converter rating. There is 300 kVA converter rating. It's a huge difference. So in that itself, we can able to save a lot of money. So that's what this is okay. But here the problem is above synchronous speed only it will act. Above synchronous speed to 1600. I can say for 4-pole machine 50 Hz system, I can able to control my speed from 1500 to 1600. I cannot go beyond this range. So the range is limited. That's advantage. That's a disadvantage with this topology. So for overcoming this speed range, they have come up with the WFIT induction generators. In the WFIT induction generators, we are having the back-to-back converters at the rotor terminals. So this back-to-back converters at rotor terminals, again the converter rating of this back-to-back converter also, it's a 30%. So as compared to the top two, here the converter rating is only 30%, right? So that's the beauty of it. So, but here we are able to inject the power in the rotor terminals. So because of that, we can make this machine as a generator during subsynchronous speed also. So subsynchronous means I can say it's a 4-pole machine for 50 Hz frequency. 1500 RPM is the synchronous speed. So in this system, below 1400 RPM also, you can able to operate as a generator to 1600 Hz super synchronous speed. That is a above synchronous speed. It's called super synchronous speed up to 1600 RPM. So synchronous speed is 1500 RPM. Below 100 RPM, you are operating as a generator. Above 100 RPM, you are operating as a generator. So what's the speed? Speed range. So what's the different speed range? So here I'm operating as a generator from 1400 to 1600. So 200 RPM. But here only 100 RPM. 1500 to 1600, only 100. But here in this topology, 1400 to 1600 is a 200 RPM wide range, right? So this below synchronous speed, that will be called as a subsynchronous speed. Above synchronous speed, that will be called as a supersynchronous speeds, right? So that's the advantage of WFIT indexing generators. So that's what people are now talking about, the WFIT indexing generators for megawatt range. Or in a high power capacities, they prefer permanent magnet synchronous generator also, because why they are preferring a permanent magnet synchronous generator means here you can eliminate the gearboxes. So that's what it's a gearless wind turbines. So in that gearless wind turbines, they prefer the PMSGs. Why? Because it can operate in a low speed, even 550 RPM to 100 RPM itself. It can able to generate the power. So depending upon that, you will get the voltage and frequency. Even if you are getting a variable voltage, variable frequency, your converters are here. So this converters can take care of the variable voltage, variable frequency to fixed voltage, fixed frequency to the grid. Okay, so these are the various generators in the variable speed wind turbines. So here the converter ratings, that's depending upon you. Just even you can vary the any converter topologies and we can propose the new topology, and that also will be a good research idea. So that's what we can, good research idea, as well as for if you are planning for entrepreneurship, then you can definitely develop this kind of converters and you can commercialize it, right? So people are working on different control strategies, different converters for this wind energy conversion system. So just we are having a lot of scope in this field, right? So here in research perspective, you can change the converter topologies and controllers and integration of the energy storage devices to mitigate the power quality issues, and all will be the topics, right? So in that perspective, we have just I'll touch in another 10 to 15 minutes, I'll touch upon some kind of research problems on the slip ring indexing machines, right? So earlier, whatever we have done, just I can explain to you. So if you find any kind of research gap in my topology, you can take up that. So what I want to convey here is no topology is 100%. Just even every topology having their own merits and demerits. So here just we have trade-off between these merits and demerits, and we have to come up with a new topology. Then you have to justify it. So even in my topology also, just you can find a lot of loopholes or demerits. Then you may work on to find the new topology to overcome the issues. So the same, the wound rotor indexing generator we have discussed, the same topology only we have taken. So in that, just we are scaling up, or you can say we had added the features in it. That's very important. So what are the features we had? It means in an earlier case, the wound rotor indexing generator, I mean, this is the topology. Earlier, it's a rotor resistance control. This is available in the literature. Even just a lot of papers they have discussed. But just we have to put some novelties and we have added some features. So what features we have added here means, if you look at in that earlier case, this resistance, the rotor resistance, just we have connected the chopper. After the chopper, we have connected the resistor. So that resistance is fixed one, right? That resistance is fixed one. But what we have incorporated is we have mentioned as a variable one. Why we have mentioned the variable one means earlier that they put as a fixed capacitor. So that fixed capacitor can be used as a just a dumping load. So they will fix, I mean, they will connect the resistor. So whatever the power it's extracting, that will be dissipated as a heat, right? Dissipated as a heat. Here what we propose is, instead of dissipating the heat in the fixed resistors, we can give it to the local farmers for crop drying, or for or you can say in a developed some countries, cold countries, they can use it for space heating applications, right? So instead of wasting in the fixed resistor, you can connect to your local loads like space heating or drying the crop and all. You can use it. So that time just I have to mention as a variable resistor. Why? Because again you are you are involving with the consumers. Consumers will keep on changing their loads. So that's what you can put the variable resistor. So here you can think of it. Here also I have to change the resistance of the rotor, but here also the load is varying. So just I have to take care of this dynamics, right? So one is this. Then another point coming to our mind, even the space heating loads or drying the crop and all, it's not available means, again, that will be wasted in our resistor, some fixed resistance. So instead of wasting it, what we have done is just connected the battery with the help of simple diode here. So even people may talk about when you are connecting the battery, you have to use some chargers and all. But this diode itself, it will act as a self-regulating switch. How means, whenever you are not having the load, what it means? That means higher resistance. The resistance is higher. So I can consider as an open load, right? You can consider as an open. If you are having the higher resistance, it's an open load. So that time your voltage is higher as compared to this terminal, this terminal, because this is connected with the positive of the battery. So if your voltage is higher, then this will be forward biased and it will start to conduct, and that current can be passed to the battery to charge. So whenever you are having the more loads, I can consider this a variable load. So you are having the more loads. What will happen? The load, you are having the more loads means it's a short circuited. Exactly, right? If you are having the short circuit. So that time here the voltage, what's the voltage at the short circuit? It's a 0. So this voltage is higher than this. So that time this will be reverse biased. That time this will be reverse biased. So it will start to discharge the battery, right? So it will start to discharge the battery, right? So whenever you are having the more power, it used to charge the battery. So whenever you are having the more loads, then this will be reverse biased and start to discharge the battery. So in that way, just we have proposed that this is the new topology. In addition to that, we have implemented speed sensorless algorithm. Earlier, for implementing the maximum power point tracking, just we need a speed information. That speed information we have estimated by using the speed sensorless algorithm. If you are really interested on that, interested in very detail about this topology, you can refer our paper that is available in IIT Power Electronics. So these are the proposed topologies. As like this, only just we have implemented the speed sensorless algorithm, and we have, instead of taking the speed from the tacho generator, just we have used the speed estimation technique by using the voltage and current sensor, and we have estimated and given to that. Right, these are the hardware setups for the wound rotor and extension generator. So even the converter, even the control DSP controller, signal conditioning circuit, everything we have fabricated in a lab, and we have tested in the. Okay, so next I can touch upon, not very much detail. Here in WFIT induction generator, we have discussed conventional. If you are looking at the conventional WFIT induction generator, always they have connect the back-to-back converter at the rotor terminals. So why they are connecting the back-to-back converters at the rotor terminals means, if you want to operate, if you look at the operating regimes of DFIM, you can able to understand it. So the top two are motoring mode. So this motoring mode we won't consider for wind turbine. So as just I'm leaving. If you are really curious to know, then you can refer the slide so you can able to understand it. So now just I talk about these two modes. Subsynchronous generation, super synchronous generation. If you look at that, if you are saying it's a generator, you have to take the power out from the stator. So here also you are taking out from the stator. Here also you are taking out from the stator. In the shaft, you are giving the input power. That means it's a generator. You are giving the input power at the shaft. But look at that power flow in the rotor. So during subsynchronous generation, you are injecting the power in, right? You are injecting the power into the rotor. So here, just we are taking the power from the stator. That's what in the topology, if you look at it, it will be understandable. But taking the power from the grid and you are injecting to the rotor coils. So the power flow is in this direction. Power flow is in this direction, right? Power flow is in this direction. So in the supersynchronous, just we are taking the power output from the stator as well as we are taking the slip power output from the rotor. So you are taking the power output from the rotor and you are injecting back to the grid. You are injecting back to the grid through the back-to-back converters, right? So here what to understand is you need some kind of source here. Instead of connecting this converter to the grid, you can use some source here and you can use with a single converter. So that's what we have done is just we have removed this part, this rotor, this grid side inverter we have removed. Why we removed means this part is used for injecting and taking the power from the grid. So here we need some power source. So by eliminating this grid side converter, just we have incorporated the battery storage. We have incorporated the battery storage. So battery storage, we can able to charge and discharge the batteries, right? Discharge the battery so that you will get the power for this converter, right? Input to the converter. So that only we have done. So what's the advantage means if you are removing the converter at grid side, you can eliminate the harmonics injection to the grid, because whatever the converter or whatever the power electronic switch you are connecting to the supply, it will pollute the system. So what we have done is just we have simply removed that grid side converter and we have connected the battery. So here this converter is not directly connected to the grid, is through the mesing. So here in the mesing you are having the winding. That winding itself will act as a filter, right? So it will eliminate the harmonics in the current. So here then here during the subsynchronous generation, you are injecting the power from the battery to the rotor. So during the supersynchronous generation, you are extracting the power from the rotor and can be used to charge the batteries. So with this topology, just we have identified different modes of operation and we have explained that. This is another paper in IIT electric power application. So just if you are really interested in this topology, you can check it out. Okay, so this is what from my side. Even the same topology we have proposed for supplying the standalone load. So here it's a power, active and reactive power control in terms of grid connected system. If you are putting the standalone loads, just you have to maintain the voltage and frequency constant. So just we can regulate the voltage and frequencies. For that, just we have changed the control strategy. So that will be another paper in IIT electric power application. So even just we have, the same way, first we have identified a problem, then just we have work on the different perspective, grid connected system, standalone system, energy management algorithms, and even control strategies. In a control strategy, if you have the one parameter, how we can estimate that parameter, that perspective also, we can start to work, right? So these are the different power electronic converter topologies for. If you have any specific questions, I will be happy to answer. Because it's time is 3:35, so I don't want to take much of your time. Already you may have engaged from the morning, so I stop it here. If you need more information, you can drop me a mail. I'll be happy to write it back. For now, if you have any question, you can ask me.
Sir, good afternoon, sir.
Yeah, good afternoon.
Thank you for your session, sir. I had one question. In that experimental setup, what you have
Madam, you interact with your resource person, madam.
Yes, sir, I'm talking.
Yeah.
In the experimental setup, what you have shown, did you emulate the wind profile, sir, by any chance, by using a PFD drive?
Yeah, we have emulated that. There are two ways. One is if you are really working on that, if you want to if you are working on an MPPT side, you have to emulate that wind turbine. If you are working on the control side, just we can do the step change in the speed and we can show the results. But better, you can emulate your wind turbine on the DC drive. So that would be better. So if you are having, just in experimental, you are having the induction machine coupled with the DC machine.
Okay.
Okay, that DC machine, you may have the, suppose if, what we faced is, actually we have implemented that, emulated that wind turbine profile in AC drive. So when we have wind turbine profile in the DC drive, we have faced the problem with the drive system, DC drive system, because we could not able to find any DC drive system. So AC drive in the market, we are having a lot of drives for V/F control and all. It's already available. So instead of connecting your induction machine and DC machine, both one machine you can have the spool cage machine, another machine you can have. Here I have worked on slip ring machine, so another machine is slip ring machine. So here you can purchase this drive turbine profile with that.
Okay, sir. Okay. So all those cut-in speeds, etc., we can emulate, right?
Everything we can emulate, everything, because just we are programming it, right? But you should ensure that your prime mover rating should be at least 20% more than your generator rating.
Okay.
Prime mover, if I say it's 3.7 kilowatt is your sleeping machine, then at least you should have 5 kilowatt in your prime mover.
Okay, sir.
So in that way, you can able to check out the cutout speed and all.
Yes. Okay. Yeah. Okay, sir. Thank you.
Okay. Any other questions?
You are having any queries? Unmute your audio and that with our resource person. Thank you, sir.
Okay, sir. Thank you.
It's a lot of practical things. Thank you very much. And Mr. Magesh, sir?
Yeah, sir.
Okay, sir.
Yeah, good evening.
Okay, good evening, sir. Okay, sir. Magesh, sir?
Shall I go for vote of thanks, sir?
Yes, sir. You go for vote of thanks, sir.
Yeah.